Oh man, this is just gonna be sick. What we're gonna start to do now is combine our knowledge of the P series, maybe a little bit of geometric series, and start to compare series together. This lesson is all about what is called the direct and limit comparison tests. So, as always, I'm gonna go over how and when to use these things for showing convergence and divergence. Now, starting out, what we have here is we know that we're given some series n equals 0 to infinity of a sub n is the series that I'm testing or that you're testing. So we're going to go over the direct comparison test in this first video of the lesson. So if I know, that's you, that the series from n equals 0 to infinity of b sub n converges, and we know that it compares well with a sub n, meaning we know that the series that we are interested in is less than or equal to a series that we know converges, then that series that we're interested in converges too. And that makes a lot of sense if you think about it. What we're basically saying is, if I have a series that I'm interested in and it is less than or equal to a known series that goes to a finite number, it converges. Less than converging is converging. And I've got that down here too. Now, the other idea is, if you know that the sum of n equals 0 to infinity of b sub n diverges instead, and we've got that the series that we're interested in is actually more than the series that diverges, then what you know is that a sub n also diverges. Okay, why does that make sense? Because we're saying that we have a known series that diverges. The series that we're interested in is more than that diverging series, and more than diverging is also diverging, right? More than going to infinity is going to infinity. Now, that is the main idea here. So just remember these quotes. Less than converging converges, and more than or greater than diverging diverges. People will often ask, well, what happens if you think something converges, but you can't find something that compares well to it? That's where the limit comparison tests come in. But this is all about direct comparison. So when to use it? Well, when I look at a series and think that is a lot like insert whatever series you're currently working on. So it's a lot like this current series that converges or diverges. So you're looking at that and you're like, whoa, this series looks like that converging geo series. Maybe it compares well to it. It's a lot like. So when you say the words, it's a lot like, you're comparing. You're kind of giving yourself the answer there, right? Comparison test. So again, two quick notes. Note that if the series I am testing is greater than a converging series, then the limit comparison test is what we want, because greater than a converging thing might also converge, or it could diverge. So if I have something that goes, I don't know, to 17 billion, but it converges to that, and I've got my current series that I'm testing that I know is more than that number, it could be finite, it could be 17 billion 1. Or it could diverge to infinity, who knows? And the same goes if you've got a test that is less than diverging. So if I have something that I'm like, I think this diverges, but it's less than a diverging series. Well, less than infinity could also be to a smaller infinity, if you will, or it could also be to a finite number. So this only works if you are less than converging, then you converge, and more than diverging, then you diverge. Okay, without any further ado, I'm going to go over this with formal justifications. So again, we're going to listen to our intuition here and be like, what is this a lot like? Well, this compares well, and I'm going to kind of put little squiggle marks, if you will. It's approximately n equals 1 to infinity of 1 over n to the fifth. It compares well to that. So I'm going to state this out loud first. This we know is diverging because it's this we know is converging. Let me start that over again. It is converging because we know that the p-value is more than 1. So this is a converging p-series. And this is less than that. So therefore, this converges by the comparison test. So how do we write all that out? You actually first want to start out with the proof that the series you're comparing this to converges or diverges. So I'll say, since n equals 1 to infinity of 1 over n to the fifth is a converging p-series. So that is a converging p-series. And you got to state your conditions, right? With p equal to 5, there it is, which is greater than 1. And now we say that's converging, and n equals 1 to the infinity of 1 over n to the 5th plus 2 is less than or equal to that series that we just said converges, then our series n equals 1 to the infinity, it's a lot of writing, of n to the 5th plus 2 converges by direct comparison. So these are probably some of the lengthier proofs, but it's very intuitive. So if you have to justify it out formally, you've got to state out first why the function, I should say, why the series that you're saying that the current series is a lot like converges or diverges. You're basically doing that proof separately. And then show that you're either less than converging or more than diverging. And then make your final statement, therefore it converges. So all I said is this is less than or equal to that. And you might be like, it's less than or equal to that? It is. The denominators are all bigger. N to the 5th plus 2 is a bigger number than n to the 5th as n goes to infinity. So we've got a smaller fraction all the way along. Slightly smaller, but just small enough. That's it. Not so bad. Now, if I'm doing this as a multiple choice problem, and I'm just given 1 over n to the 5th plus 2, I'm looking at that and I use what I call the inkling test. It's where I get an inkling and I'm like, n to the 5th plus 2 is basically n to the 5th. That's a converging p-series, so this is too. This is just how to do it formally and how to justify your answer. Isn't that awesome? I think so too. All right, so this one right here, I look at that and I'm like, this is a lot like 1 over root n, right? Which is the same as 1 over n to the 1/2. Oh, we'll start it at the same exact value, so it compares perfectly. So this is a diverging p-series. So we're thinking this one probably diverges because it's not off by much. So I'm going to start out with my proof or justification that this thing diverges, since the series from n equals 2 to infinity of 1 over root n is a diverging p-series. So is a diverging p-series, and I'll just put here p equal to 1/2, which is less than or equal to 1. So now I've shown that this series diverges, and I've got my series here is actually more than diverging. That's what we're looking to do here, be more than diverging. And I'll state why that is in a second. So 1 over root n minus 1 is actually greater than or equal to the sum from n equals 2 to infinity of 1 over root n. Then our series, just copying that down again, n equals 2 to infinity of 1 over root n minus 1 diverges by direct comparison. That's it. And you could say by direct comparison test as well. So the sequence of logic here is, we look at this thing, we say, oh, this thing is a lot like 1 over root n. Sweet. That's basically 1 over n to the 1/2, which is diverging. Now we need to show that the series we're interested in, this John right here, is greater than or equal to this John. And if you're not from the Philly area, John means this thing and that thing. So this right here is more than or equal to that. Why? We have n minus 1. It's just slightly smaller as a denominator than this is, making this slightly bigger. So we are now more than or equal to a diverging series. And more than diverging is also diverging. That's it. So we show that the thing that we're comparing to diverges. We justify that. Then we show that the thing that we think also diverges is more than that. Therefore, we're making our conclusion diverges by the name of the test. So the conditions, conclusion, name of the test, as always. Oh, isn't that just awesome? I think so. Now, in the next video, we're going to talk about the limit comparison test, but I just wanted to put this at the end of this one. Because here's the thing. What happens if instead we had like root n plus 1, where we're thinking, well, root n plus 1, that's slightly less than this. Slightly less than diverging. Does it diverge? Because less than infinity could be finite too. So with the inkling test, you'd look at this thing and be like 1 over root n minus 1 or plus or minus any numbers, basically this at infinity. So if it's multiple choice, you're like, yo, bro, this thing diverges because that does. But doing it out justification-wise, we can only use direct comparison here because we're more than diverging. What happens when we're not? As I said, limit comparison. All right, I'm out. That's enough of me talking. I'll see you in the next video. Until then, peace.